you know, I talked about, how some integrals, how we need integrals in order to solve some differential equations. And, I mentioned some differential equations containing, some in such form, containing some constants, and I said that m could be any integer. And now here I want to talk about where such differential equations came from. And, for instance, here, if you plug 1 into m, this becomes minus 2r. If you plug 2 here, that becomes minus 6r. And these are the same. We got infinity number of such differential equations, which could be derived by plugging positive integers into n. Now here I want to talk about where do they come from. And here the capital R, this is in polar coordinates, and the capital R is a function of the little r, and by solving it we want to find the function capital R. Okay, so it appears in solving this problem, the following problem. We got a ring, circular ring. Which mass is n. This is a ring, and its radius is c. Mass is n. And, in nature we don't have a real ring, because everything got a thickness, some thickness, but here the thickness is very small, and we want to calculate the gravitational potential at every point around it. We usually work with potentials because, for instance here, the potential, and potential energy is different than potential, I talked about it for the charged particles before. I talked about the potential energy. We got some particle which charge was Q1 and another was Q2, okay, and the potential is the energy over Q2, and the potential due to this particle around it is this, okay. This is potential energy and this potential. Okay, we use with with potentials because, for instance, in three-dimensional, the x component of the force, gravitational force, equals to minus the derivative of potential energy, say, with respect to x, and the y component of the force is minus the derivative of the same potential with respect to y, and the z component of force would be minus the derivative of potential with respect to z. Here here u is a function of x, y, and z, three variables. Okay, because forces are vectors, adding and subtracting them needs the crazy vector adding and subtracting, but potentials are numerical functions. The usual numerical functions we have dealt with so far. And another thing is that here we, for the points on the axis of the ring, this, okay, according to the symmetry, to every points on the axis, every points of the ring are the same. Here we could calculate the potential easily, but for the other points on the space, we don't have the symmetry, and in order to find the potential, we need to solve this differential equation, and this is in the polar coordinates. The second derivative of r times v is the potential over dr plus 1 over sine theta okay, here this is plus the derivative of sine theta, derivative of v with respect to theta, derivative of this with respect to theta, okay, equals to 0. This is our differential equation. And the reason I wrote it in the polar coordinates is that if this equation in the Cartesian coordinates containing the derivative of v with respect to x, y, and z, three variables, but here we just got the derivative with respect to two variables. I talked about it in the polar coordinates videos. Okay, and one thing here is that before I told you, that the potential energy is, something like this. The integral from minus infinity to f, the final point, of the force dr. Okay, now what is this? If the potential energy is this, now what is this? And the thing is that you could derive this tree from this or this from this tree. Okay, and I forgot to mention it that the potential of the points on the axis equals to, we could derive that, I'm not gonna do it here, equals to the mass of the ring over the square root of c squared, c is the radius, plus z squared, and z is the distance of the points from the center. Okay, and so this is for the points on this axis. Okay, but for the points on this axis, theta equals to 0. Okay, so this is for theta equals to 0. I talked about the polar coordinates in 3 dimensions, or the spherical coordinates, in which theta is the angle. For instance, suppose take some point on the red marker. The theta is the distance, is the angle between these two. Okay, so for the point on this, theta is 0. This is another thing for this differential equation. So now how should we solve this? And here r and theta are independent, unlike the polar coordinates in 2 dimensions, which r was a function of theta. Okay, so now in order to solve this, we suppose that v be a function like r times theta, the big R and big theta, in which r is a function of just r, the little r, and the big theta is a function of just the little theta. And this is a product